Phosphorus trichloride reacts with chlorine gas in the gas phase to form phosphorus pentachloride in the formula given here. And in this particular problem, we're told the initial concentrations of not only the two reactants but also the product, which means that what we have to do first is we have to determine the direction of the reaction. And only once we have determined the direction of the reaction can we then solve an equilibrium problem to ultimately get the equilibrium concentration of the chlorine gas. All right, so two steps: do the direction of reaction and then solve the equilibrium problem. All right, so how do we determine the direction of the reaction? Well, the first step is to basically use these initial concentrations to calculate the reaction quotient. So if we do that, we would be taking the reaction quotient, which is going to be the concentration of the PCl5, all right, in this case it's 0.399, and we're going to divide that by the concentration of the PCl3, which is 0.485, and the concentration of the chlorine, which is 0.261. And when we put this into our calculator, and I'm going to save you the steps of doing that, but when you put this into the calculator, we find that the overall value of this is 3.152. Now the problem tells us that the equilibrium constant is 0.5. So in fact, this is greater than the equilibrium constant in this. So we have the classic situation where Kc is less than QC, so that means the reaction proceeds to the left. Now we could have also done this by doing this on a number line, where we would have had Kc appearing here at 0.5 and QC over here at 3.152. So once again it tells us that this reaction must move to the left in order for the reaction where it is to end up at equilibrium. So when we set up the ICE table for this, we're going to set up our three chemicals that are part of this reaction. And then we're going to indicate the initial concentrations, the change, and then the equilibrium concentrations. So initially we have PCl3 is 0.485. Initially the chlorine gas is 0.261. And initially the PCl5 is 0.399. Now since this is going to the left, that means we're going to lose our product PCl5. So we're going to have a minus x here. We'll have a plus x here and a plus x here. So when we put all of these together, we have to add I and C together to get E. We'll have that the equilibrium concentration of PCl3 will be 0.485 plus x. The equilibrium concentration of Cl2 will be 0.261 plus x, and the equilibrium concentration of PCl5 will be 0.399 minus x. All right, so now what we'll need to do is plug this into our equilibrium expression. So we know that the equilibrium constant is going to be the equilibrium concentration of PCl5, 0.399 minus x, divided by the equilibrium concentration of PCl3, 0.485 plus x, and the equilibrium concentration of Cl2, 0.261 plus x. Now we could expand this out and write it as a quadratic equation and use the quadratic formula to solve it. However, what I'm going to recommend is that you use Wolfram alpha. And if you go into Wolfram alpha and you simply type solve, and then following the solve you type 0.399 minus x over, and then use two parentheses, 0.485 plus x, close parentheses, and then another open parentheses, 0.261 plus x, and then close all those parentheses, and then equals to 0.5. And if you hit return, then you will get the answer that comes out. Now, it may be that the answer will be given to you in terms of some square roots. Then you would simply click on a thing that basically gives you approximate forms, and that will give you a numerical answer that you can use. Now, it turns out when you do all of this, Wolfram alpha will tell you that x has two values. One of those values is a negative number, but it's a very large negative number that if I were to add it to either one of these, I would get a negative concentration. So I know that that can't be the right answer. The other answer is a positive number that is less than 0.399, and so that's going to be the one that actually is the right answer, and it'll be 0.22592. All right, so this tells us where the equilibrium position for this reaction is going to be. If I want to know the exact concentrations of all of my reaction species at that, I would need to plug this value for x into these three different concentrations here. All right, so if I were to simply round this off at 0.226, I would find that the equilibrium concentration of PCl3 would be 0.711, the equilibrium concentration of Cl2 would be 0.487, and the equilibrium concentration of PCl5, let's see, would be, drum roll please, 0.183. All right, and then if I want to check my answer to see if this is reasonable, I would just put this back into my equilibrium expression and calculate what this gives me. It should give me the equilibrium constant. As it turns out, by rounding off here, we end up with a number that's 0.528 or 529. So it's a little bit larger than our actual equilibrium value. So these things can be very sensitive to the number that you get out. All right, if I had plugged in exactly this number, then I would have gotten something much closer to the equilibrium value. In fact, it would have been almost exactly equal to the equilibrium value. All right, so just a little bit of lesson about significant figures. This is the number of significant figures, by the way, and 0.226. However, if we use more than the significant figures, we'll actually get something closer to the actual equilibrium value. All right, so what were we asked for in the problem? We're asked for the equilibrium concentration of Cl2. Well, that's given right here. So this would be the answer to the problem, and you've now seen how to work it using an ICE table.